Today I want to talk about some wireless power transfer experiments I've been doing of late. This all started when I wanted to build one of these rotated display, persistence of vision display gadgets. This is the prototype. Most people use batteries or steal power from the motor armature that rotates it to power the electronics of the actual display. I thought we could use some little bit of RF technology to send power across the rotating gap. Anyway, more on that later. The basic outcome of all of this is that we've built a simple little prototype here that can send power wirelessly several coil radii with little effort. If you wanted to power your laptop with this kind of approach, you'd need fairly large coils if you wanted to, say, sit on the lounge and have the transmitter built into the wall or across the other side of the room. So I want to do some basic research and study of the phenomena and work out how it works and how we can optimize it for sending power to more macroscopic amounts of power. I mean, this is obviously just a LED, it doesn't take a lot of power, but several watts, say, so that you could perhaps charge a cell phone without having to have it sit directly on a charging cradle, or some similar other practical device would be an actual use for this technology. Right, so what we can see just with this simple low efficiency lash up is that coupling is very important. As we increase the distance between the coils, coupling drops off quite rapidly. Also note that the coupling out here is still reasonably good, and there's this interesting little crossover region where the coupling actually drops through zero. Also, if you put the coils orthogonally, as you'd expect, everything cancels and you get no power transfer. This all comes from the basic electromagnetics of the system, but I thought it'd be interesting to talk about that first before we move on to how to optimize this for transferring significant amounts of power. To study the coupling between coils, I wound myself two experimental coils. These particular ones are called C and D because they're the third and fourth ones that I made. They're about 4 microhenries, and they don't have particularly good Q or self-resonant frequencies because of their physical construction. Their wires are quite thin and they're quite bunched up laterally on top of each other, which gives them a lot of distributed capacitance. But using these, I performed some basic experiments like measuring the coupling as I separated them with it by distance, and also axially. This is the resulting graph that shows, well, the details are on my website, but essentially once you get beyond about a radius apart, the coupling drops off very rapidly indeed and approaches zero. There's also this interesting region where the coupling goes negative because the flux area here is much coming through from this coil up, if you like, through into this coil, is getting smaller than the flux that's coming from the other side of the coil up through this larger area, even though the field is less dense out here. So even though the coupling coefficient goes negative, this is just a mathematical thing. For our power transfer purposes, this doesn't really matter. You're just getting energy from the other side, and you'll get reasonable coupling out here until eventually the field tapers off to nothing. So, what does this mean for practical application? Well, even though the quality factor of these coils is not particularly good, the fact that they're planar means that geometrically they're quite easy to integrate into a device, say a cell phone or a laptop, something like that, and they can be placed quite close together, which gives us good coupling coefficients if we can place them directly on top of each other in a charging situation, for example, say a charging mat. And this enables us to have fairly high efficiency even when they have poor Q. Now, I have some other inductors that have much better Q. This, for example, is an inductor that was built specifically for high Q. It's made out of thick wire. It's space wound, so there's a gap between each coil, and we'll talk more about why that's important later. And it has approximately the right length to diameter ratio, which is also important for high Q. This coil has a Q over 200, whereas these coils here have Qs that are about 65 if they're lucky. The difference is quite significant when it comes to high efficiency power transfer with very low coupling coefficients in, say, a wireless electricity transmission system where you've got the coils very far apart. To understand more about how wireless power transmission works, unfortunately we need to do a little bit of math, or at least a basic understanding of the electromagnetics of the situation. Here I've got some diagrams that kind of explain the basic induction principles, where one inductor can transfer energy to another inductor in space. First we start with Ampere's law, which basically says that wherever you have a motion of charge, a current, you have a circulation of magnetic field associated with it, and that the strength of the magnetic field is directly proportional to the amount of current that passes through the conductor. If you combine this with Faraday induction, which says that whenever you have a change in a magnetic field, you have a voltage produced across a conductor that's enclosing that magnetic field. And Lenz's law, which tells us about the sign of direction that the induced voltage and current will flow, it always flows to resist the change in the magnetic field. So if you have two inductors situated above each other and you ramp up the current in one, which increases the magnetic field, the current in the other will be in the opposite direction, such as to produce its own magnetic field which opposes the change in the magnetic field of the driven coil. This is the basic principle of the transformer. Now, transformers come in many shapes and sizes. The ones you're probably familiar with are designed for high efficiency in low frequencies, and they have a big metal core that encloses the loops of flux so that they have a very high coupling between the primary and the secondary. With our particular power transfer application, we don't have that. The coupling between the coils is very, very weak. As we showed, the coupling coefficient is generally below 0.1. Whereas with the transformer it would be 0.98 or higher. There'd be very little leakage flux. Now this leakage flux causes a lot of problems. Problems that can, well, we can get around, but we have to do some pretty special engineering and pay attention to losses to make sure that we can actually transfer power between two weakly coupled coils at high efficiency. This is a typical mains power transformer. As you can see, it's quite heavy. It's made of silicon steel laminated pieces that contain the magnetic field between the primary and the secondary winding, and give it a very high coupling coefficient between the primary and the secondary for efficiency. Contrast that with our power transfer system, where we have only essentially the vacuum of space between, and the windings are situated quite far apart, and as we saw with the experiment where I actually measured the coupling coefficient between two inductors, it's very weak, and this leads to poor efficiencies unless the coils have a particularly high quality factor. We'll talk about that in a minute. Let's talk about the ideal transformer. The ideal transformer is a mathematical model that's utilized to describe and study systems of transformers of real-world coupling, but it's useful from a mathematical point of view because we can reduce the ugliness of a real transformer to an ideal transformer plus some external components to make up for the leakage inductance and resistance, capacitance, etc. The ideal transformer's properties are purely defined by the turns ratio between the amount of turns on the primary and the amount of turns on the secondary. The windings are assumed to be so tightly coupled together that they have a coupling coefficient of 1, so that all of the flux from the primary makes into the secondary and vice versa. So the only thing that determines the current transfer between one side and the other, and the voltages that you see across the windings if they're open circuit, is the ratio of the turns. This also means that any impedances that are seen through the transformer are related by the square of the turns ratio, not just the turns ratio. This is because of the nature of impedances versus currents or voltages. Also note that if you step up voltage, you step down current, and vice versa. This is used, very practically in devices like this, which is designed to take 240 volt AC and turn it into 6.3 volt and center tapped, but we don't need to worry about that at the moment. In our particular case where we have very weakly coupled inductors, we have a coupling coefficient. It's called K generally, but it is essentially a percentage of the amount of flux that comes from the primary and the secondary, the shared flux, if you like, between the two windings. All the rest of the flux is leakage and doesn't constitute the transforming action. It appears as an additional inductance in series with the primary and the secondary, which is called the leakage inductance. Now, leakage inductance is really annoying because it drops voltage across an AC signal trying to make it through the transformer, and it reduces the amount of power that we can transfer across without using special techniques. Now, the mutual inductance between two windings, which can be found by measuring the inductance of each inductor separately, and then with them in phase or antiphase, we can measure the extra inductance that we get, or the extra inductance that we lose, by having the two windings coupled together magnetically. This is called the mutual inductance, and it's quite easy to measure. You can just take two inductors like this, which is exactly how I did the experiment I spoke about before. I measured their inductance separately, and then I combined them together and I wired them up actually antiphase, and measured the inductance again as I separated them. Now, the inductance difference that we see, if they were separated, we would expect them to just add together like normal inductors do, and we would see about 8 microhenries instead of 3.9 or whatever these are in isolation. But we actually see less than this because the mutual inductance between the coils cancels, and by various mathematical techniques you can work out how much mutual inductance you've got, and the coupling, or the amount of flux that's being spilled instead of coupling from inductor to inductor. Inductance is very important. It's a property of charge. It's essentially like induction that we spoke about earlier, but instead of having two windings, it's essentially the effective charge and the magnetic field that it produces interacting with the charge carriers themselves in adjacent wires. I mean, even a straight piece of wire has inductance. It's a physical property of the speed of light, essentially, that the current produces a magnetic field. The magnetic field can only move at the speed of light, and it interacts with charges that are in the straight piece of wire. But coiling up the wire concentrates the magnetic field, because the magnetic circulation concentrates into the center of the coil, as I've drawn here. Note that not all the flux makes it through all of the turns in the coil, and this flux that only makes it through part of the coil is what gives you the rest of the field around the actual edges of the inductor, and makes it particularly difficult to calculate the inductance of a real inductor. But there are various mathematical approaches to modeling this leakage flux, and we can get some pretty good results. We'll talk about that later as well. But the important thing about inductance is that inductance resists the change in current. When you try and ramp up current, or stop a current, or turn it on, turn it off, etc., any kind of change in the amount of current flowing in a conductor, the change in magnetic field through Faraday induction and Lenz's law produces a corresponding voltage that resists the change in current. So we call this inductance, and it's called L generally. It's the coefficient that relates the time rate of change of current with the voltage that you see across an inductor, and conventionally the voltage is seen to oppose the current. Okay, so inductance and coupling and things like that, it's all great sounding theory, probably boring you to death, but what does that mean for our power transfer system? Well, power being transferred, say, from a generator to a load, it's quite simple. Ohm's law applies, everything works. If we put a transformer in the middle, an ideal transformer, again, there's not a whole lot of difference. All of the current that goes in comes out, there's no losses, no complexity associated with transforming the impedance that we see back at the generator, and again, it all works. But in our system, where we have a very small coupling coefficient between windings, then the inductances are no longer completely hidden by the transforming action. You start to see the leakage inductance of the primary and as part of the circuit of the primary. This I've written out here in a, well, I've hidden a few steps, but essentially what you can do is you can remove the coupling coefficient and replace it with an ideal transformer and a leakage inductance and a magnetization inductance, which models what's really going on in the weakly coupled coils that we showed you earlier. The important thing to note from this is that there is an n/1 turn ratio between the primary and the secondary now, and this inductance here, the leakage inductance, is quite large. It's quite a significant fraction of the inductance of the primary if the coupling coefficient is really small. The magnetization inductance is quite small, and we can generally ignore that, but it's important to know that it's there. And the turns ratio of this, theoretical transformer that we've put in here to model the imperfect coupling goes by the coupling coefficient times the square root of the ratio of the primary and secondary inductances. The important thing to know about this is that this number is going to be quite small if K is quite small. So our resistance, when we transfer it across the transformer and remove the transformer, which is what I've done over here, is going to be, its impedance is going to be transformed by this number squared, and that's going to be a very, very small number indeed, which means that this resistance is going to look really tiny. Essentially, from a physical point of view, when we're talking about coupling between a coil and another coil, when there's very low K, this coil won't see a lot of this coil. It seems quite straightforward from a purely intuitive point of view. The closer you put it together, the stronger the coupling is between them, and the more of whatever load that you put across the end here will be seen by this coil. But as you separate it, what is seen here gets quite small. Now, also annoying is this inductance term that we've got. It's quite large with respect to this now tiny load that we're seeing. Ignore this magnetization inductance for a minute. This inductance really prevents us from sending a significant amount of power into this resistor. We can get around that, however, by adding some capacitors. Resonance is a wonderful thing, and here it really is our saviour. We can tune out this magnetization inductance with a little bit of capacitance, so you can essentially ignore that part of the circuit, and you can tune out this inductance with another capacitor here. So this cancels. Unfortunately, if you just did that and didn't add this capacitor, you'd be left with a situation where the generator sees n squared R, not R, and it's going to see a very, very small resistance and probably can't transfer much power to it, because another thing that we haven't talked about here is source impedance, but for simplicity I'm ignoring that. What we can do, however, is we can add another capacitor here and reduce this capacitance so that we have a little bit of inductance left over to resonate with it, and transform this n squared R impedance to our original resistor impedance that we wanted in the first place, and transfer power to the load just as if it was physically connected. Of course, that's all in theory. The real situation is a little bit more complicated because practical components have losses, and in this particular case the losses really hurt us because the losses start to look quite large with respect to this n squared R term. Now, I'll explain that in more detail. Real inductors are not the pure magnetic devices we were talking about previously. Real inductors have physical losses because they're made out of wire. Now, copper is the most common material. Copper is a reasonably good conductor. Silver is better, and obviously there are superconductors, but we won't go into that. The amount of cross-sectional area of the wire tends to denote how low a resistance it will have. The fatter the wire, the more electricity it can conduct for the same voltage drop, the same resistance. But at AC things aren't quite that simple. At AC we have things called the skin effect and the proximity effect, which make the resistance of the actual material that the coil is made out of worse than the pure ohmic losses that we see at DC. When we pass a current through a wire at DC, all of the current is shared over the entire volume, the entire surface area of the wire, of a cross-section through the wire. In AC, because of the inductive principles that we saw earlier, the current tends to redistribute itself to only be in the outer skin of the wire. This is called the skin effect, naturally enough, and it means that the AC resistance of a wire is quite a bit larger than the DC, purely DC resistance. The effect gets worse with frequency, and the higher the frequency you go, the more the current is redistributed towards the outside of the wire. And at very high frequencies and ultra high frequencies up into the microwave region, the skin gets very, very thin. And silver plating becomes quite popular because silver is a better conductor than copper, and naturally silver is quite expensive, but you can plate it onto cheaper metals and it will work just as well, because you only need a thin layer to conduct it, because that's where almost all of the current actually is flowing. This is also why tubes are quite useful in very high power equipment, because they're hollow. You don't actually need the copper in the middle of the conductor. You only need it on the actual surface where the current is flowing. And also, even right down here at mains frequencies, the skin effect is actually significant, although it's not seen in small devices like this. In power distribution systems, bus bars are generally not made much more than about 8 to 16 millimeters thick, because that's about the skin depth of 50 Hz energy in copper. It's actually a little bit worse in iron, because the magnetic properties of the substance carrying the electrical energy also affects the skin effect. Another effect that really hurts us with inductors is the proximity effect. The proximity effect is another redistribution of current effect. Essentially, currents that travel near each other will tend to push the charge away from the current, and it redistributes the current flow into even less material. So what you see all through this is a reduction of the amount of cross-sectional area of the conductor carrying current, and this increases its AC resistance. Another loss in inductors is radiation. Radiation only really becomes significant when the inductor is physically quite large with respect to the wavelength of the energy that you're passing through it. The effect is generally related to the wavelength. At very high frequencies, quite physically small inductors can radiate quite a lot of energy. At very low frequencies, in the case of our device here, this is operating about 14 megs, which is in the middle of the high frequency spectrum. This inductor is quite small, but 14 to 15 megahertz is about 20 meters in wavelength, and this is obviously nowhere near 20 meters, so it's not going to radiate very much. We can essentially ignore the radiative losses at these kind of frequencies, but radiative losses become much more annoying at very high frequencies and above. Radiative losses for power transfer applications are not a massive issue if you keep the frequency low, but it's an unfortunate consequence of the physics that the ease at which you can transfer power goes up with increasing frequencies, but the utility becomes more complicated. The end result is that the ideal frequencies to transfer power across distances that would be, say, a living room or something like that, is in the HF region. So all of this means that building a real inductor, you have to think about these losses, and it's the reason why inductors that are shaped like this are better than inductors that are shaped like this, purely because the wire is thicker, so there's more volume for the current to pass through. It's spaced out so that there's less effect from the proximity effect. And also another thing is self-resonant frequency. It's not terribly important, but for our applications, but the self-resonant frequency can become very important in other circuits. The capacitance that this coil sees from the conductor that the actual coil is made out of is much lower because it's spread out. Capacitance increases as you increase the surface area between two pieces of wire and you get them closer together. So if you spread a coil out, it has less self-capacitance and hence it will have a much higher self-resonant frequency. The self-resonant frequency of this inductor is beyond 108 megahertz. I couldn't actually measure it. It's with the particular lash-up that I was using to measure it. This one, even though it's physically quite small, because the windings are so close together and there's quite a lot of surface area in close proximity, its self-resonant frequency is only 11 megahertz. And this would be unsuitable for use in this system because it would actually start looking capacitive at 14-15 megahertz, which is what this operates at. It no longer acts as an inductor, and it also has a terrible Q once you go above the self-resonant frequency. We'll talk more about that later as well. So you want to wind practical inductors for any purpose, not just for wireless power transfer. Inductance is proportional to the cross-sectional area of the inductor. The physically larger you make it, the more inductance it will have. The physically larger the area that it encloses. Also important is the amount of turns. If you double the turns, you multiply the inductance by 4. It goes by the square of the amount of turns. There's obviously some constants that reflect the geometry of the coil and the amount of leakage flux that I was talking about earlier, and the length. You can ignore just know that there is some number. It's actually quite an ugly number depending on the units that you're using to measure the diameter and the length, but the amount of turns is just the number of turns. That there's nothing special about a turn apart from that it's actually enclosing an area. And the length, if you stretch an inductor out, you reduce its inductance. If you push it together, you increase its inductance. This is actually used to fine-tune inductors quite a lot. And it also gives us a limit on how to make high-quality inductors that have a very high Q. Q is proportional to the inductance, but inversely proportional to the loss resistance of the inductor that we were talking about. This means that to make a high Q inductor, you try to make as much inductance as you can for the least resistance. This is complicated by the fact that inductance is proportional to the area and inversely proportional to the length. So to the actual amount of matter that you use to make the coil and the physical volume of the coil tends to give you the Q. So bigger coils tend to be higher quality. It's unfortunate because they weigh more and they take up more room, and also unfortunate is the actual physical shape of the coil. Inductors like these tend to have higher quality factors than inductors like this. Although inductors like this are obviously far more convenient for power transfer applications. Now that we know a little bit about Q and quality and building real inductors, let's talk again about what we need to make an efficient power transfer system, wireless power transfer system. If we go back to our model of having a weakly coupled transformer, and now we put in our loss elements. This is the resistance of the primary winding, this is the resistance of the secondary winding, and this is our actual load resistance that we want to send power to. Now, ignoring all the capacitors and everything that I spoke about actually getting power across from point A to point B, let's talk about just the secondary side for a minute. It's kind of obvious that if you apply a voltage across two resistors, you have a resistive divider. And for a fixed amount of voltage, the most power will be delivered to this resistor when this resistance isn't there at all. So if you want to optimize the power delivered to the load, you want to make this loss really small. Now the Q of the secondary winding is inversely related to this resistance. This resistance gets bigger with the worse Q that we have. So to make this resistance as small as we possibly can, so that the actual load resistance is large with respect to this loss term, then we want the Q of the secondary to be as big as possible. Now, That sounds easy, but unfortunately it's not. From an engineering point of view, making high Q inductors is expensive because you need a lot of matter, you need to use high quality matter, copper or silver, and you need to physically use a lot of volume, make the coil very big to make as high a Q as you can. Interestingly, from a purely mathematical point of view, the Q of the secondary is nowhere near as important as the Q of the primary. This is not immediately obvious, but when you do the math it becomes quite important. If we ignore the loss of the secondary for a minute and we talk more about the primary, the transforming action of the whole system, so this load, if you like, has now been reflected into the primary coil, and we can sort of ignore it. We can just consider that it's now making up part of the resistance that the transmitter circuit sees. We can mathematically do this, and we find that the resistance, I've called it R prime, that the primary sees looking into this load across the transformer is proportional to K squared, which is the coupling coefficient, times the ratio of the inductance between the primary and secondary, times the amount of resistance that's hung off this, including the loss resistance, but again we'll ignore that. This K squared, if our coupling is quite low, like on the order of 0.1, K squared is even smaller, it's 0.01. The ratio of inductances, say we use the same inductance, we can just call that 1. It's obvious that this resistance that is reflected into the primary is going to be very, very small. If it's, say, 100 ohms and K is 0.1, then it's going to be 1 ohm. And this RP term now starts to look pretty darn big with respect to the resistance that we're seeing reflected across the transformer. So this is where the Q of this side of the circuit has to be very large, ideally as large as you can make it, because it is far more important than the secondary Q in a lot of ways, because of this transformation of this resistance to an even smaller value on this side of the circuit. In a lot of ways this is like a loop antenna. Loop antennas suffer the same problems, although for them they're trying to pump power into the radiation resistance. If this was a loop antenna and it was physically large, or a bit larger with respect to wavelength, the radiation losses that we talked about earlier with inductance is proportional to the size of the inductor. When you make the inductor small with respect to the wavelength, the radiation losses get very small, and that loss term, which in this case we want to optimize radiation from a loop antenna, becomes small with respect to the loss resistances in the actual copper that the wire, or whatever the wire is, and pipe, whatever you're making your antenna out of. This is a very similar situation, except we don't want radiation. We want to couple in a loss term that's actually the load, but it's on a similar order of magnitude to the situation where we have a radiation resistance as opposed to a load resistance. It just happens that the physics puts the load in a similar order of magnitude as the losses associated with radiating from a physically small antenna. And now we'll talk about the final wrinkle. Q, the quality factor that we spoke so much about, also is a measure of the narrowness of the resonance of a system. The higher the Q, the narrower a range of frequencies it responds over. In the case of our wireless power transfer system, it means that the primary and the secondary have to be resonant at almost exactly the same frequency, and this becomes very critical as Q goes up. If Q is about 100, which is easy to achieve, relatively easy to achieve with cheap material, then the inaccuracy of your tuning is allowed to be about 1%, so roughly the reciprocal of the Q. But if the Q was, say, in the thousands, to make the system nice and efficient, then your frequency tuning becomes far, far more precise, precision is required. Otherwise, you'll transfer very little power. And I can show quite easily by detuning the transmitter. As you can see here, it's got a variable capacitor that's used to resonate the primary. If I detune it significantly, the power transfer drops off very, very quickly. This is a big engineering challenge. If you're building, thousands of laptops, they all obviously come from a factory that manufactures the components with some tolerance. The coil in particular will be the hardest part to make. Have the same inductance, be physically the same volume, even if it's wound by machine. It's very, very difficult to put that kind of high tolerances on an inductor. The secondary, fortunately, is not too difficult, and we can, as we saw, the Q of this side is not as big a deal as the Q of the transmitter, although it is obviously still quite important. A very poor Q over here and you've undone all the good work that you might have done with the transmitting side. High Q of the transmitting side is also important because the transmitter tends to be on for longer, and circulating currents in here are very, very large. Huge, in fact, that a transmitting system that would deliver, say, 100 or 1,000 watts across the room would have such enormous circulating currents in here. It would actually make a fairly good heating device. You could probably melt an iron bar stuck in the middle if it was at a frequency that the bar would absorb quite readily. The whole mechanics of keeping this system tuned up and working in all the different possible orientations and it's a very, very difficult engineering problem, and this is probably why wireless power transfer systems have not been used in anything other than toothbrushes and chargers for phones, where you can control the geometry well, you can make sure they align with each other perfectly, and you can minimize those problems. I mean, obviously the fluctuation in the coupling coefficient detunes your entire system. I sat down with Spice and did quite a lot of simulations, and with all of those simulations you tweak K even by a few percent, and you have to change all the capacitances of the system to tune it up again to optimize the power transfer. This is such a difficult problem that I don't think that general power transmission systems where you can sit down with your laptop on your lap and have the antenna sitting over in the corner of your room, I don't think that'll ever really be practical, because it's just such a difficult problem, unfortunately. Yeah, thanks for listening.